Hello and welcome back. This is our second video in Klein Organic Chemistry Chapter 7, and we'll be discussing naming and a few properties of alkyl halides. Alkyl halides are compounds that have a carbon or an alkyl group bonded to a halogen, okay? And so in order to name them, we're going to use the same rules that we used before. We're going to find and name the parent chain, identify and name all of the substituents, so we're going to learn how to name those halide substituents in this section, assign a number to each of the substituents, and then assemble the name alphabetically. So the halide group is a key substituent we're going to name and locate in this section. So don't forget the parts of a name of an organic molecule, and that is the parent, goes in the middle, okay? Any unsaturation goes after that. Functional group goes at the end. All right, and then we have substituents before the parent and stereochemistry out in front. All right, so in this example, we're actually identifying and numbering the parent chain. So for this molecule, let's call this molecule A. The parent is 1, 2, 3 carbons, so that's propane. So this molecule would be 2-chloropropane. So for the halogens, well, they're named as fluoro, chloro, bromo, and iodo as substituents, okay? All right, and so the next molecule has 5 carbons in a chain, okay? And it has a bromine at the second carbon. Remember, we want to give our substituents the lowest numbers possible. So this is 2-bromo, and it also has a methyl group, 2-methylpentane. The next molecule has some stereochemistry. So we want to give our substituents the lowest numbers possible. We want to give our first substituent the lowest number possible. So we're going to start numbering on the left, okay? And so because our methyl group is the first substituent, if we had started numbering on the right, 1, 2, 3, then the bromine would be our first substituent at the third carbon. So the methyl group is at the second position, so we're going to start numbering from the left. We have a 7-carbon chain along this red path, and so that's going to be a derivative of heptane. We have 3 methyl groups at the 2, 3, and 3 positions. So this is 5-bromo 2,3,3-trimethyl heptane. Why is it in that order? Because bromo comes before methyl. So we don't use the prefixes for alphabetization such as di, tri, tetra. So we're comparing B with M. So this is 5-bromo because B comes before M, 2,3,3-trimethyl heptane. Now this is the R configuration of this molecule because we have the hydrogen going back. That's number 4. Bromine is going to be number 1. And this is going to be substituent number 2. This is going to be substituent number 3. Okay, and so that's going to be 1 to 2 to 3. So if you don't know how to do that, you can review the video on R and S configurations. And we'll practice some more with that a little bit later on. All right, and so we can give these sometimes a common name as well as a systematic name, okay? So this is a very strange way to draw this molecule here on the left. This molecule has a carbon with 2 hydrogens and 2 chlorines. Okay, so this is dichloromethane because it's 1 carbon in the main chain. Okay, so this molecule also has a common name, methylene chloride. And sometimes these common names just predate the understanding of the real structure of the molecule. That's why they still exist. They just caught on. So this molecule is chloroethane here, and its common name is ethyl chloride. So these common names have been in the literature so long that they just stuck and they're used more commonly than the actual IUPAC name. So we can try naming some of these molecules. Let's try to give these some reasonable names, okay? So our parent for this molecule on the left is 1, 2, 3, 4, a derivative of butane. But to give our substituents the lowest number, we can actually go from either direction, but going from right to left, 1, 2, 3, 4, we're going to have our substituents numbered as 2, 2, 3. Going from left to right, it's going to be 2, 3, 3. So the top way beats the bottom way, okay? So we're going to go along the blue path in order to number our substituents. So we have 2 bromo as a substituent, 2 iodo as a substituent, and 3 methyl along the blue path. And then we just alphabetize them. So that would be, remember our parent then is butane. We don't have any unsaturation, and we don't really have any functional groups here that we need to be concerned about, so we're just going to use the ANE ending. We just have prefixes that are the substituents, so that's going to be 2 bromo, 2 iodo, and we put hyphens between the numbers and the letters, 3 methyl butane, okay? But we also have stereochemistry here, and therefore we're going to need to determine whether this molecule is R or S. This is really a challenging configuration for this molecule to determine the R and S configuration. And another thing that we need to consider is, which comes first, which has a higher atomic number, bromine or iodine, okay? So we need to figure that out. So remember, we have fluorine, chlorine, bromine, and iodine on the periodic table. So iodine is higher than bromine, okay? And so I don't remember what those exact atomic numbers are, but you can look those up on a periodic table. I forgot to bring one up here. Okay, and so let's see. So let's erase some of this so that we can name this molecule properly with its proper R and S configuration. Okay. All right. So we're trying to figure the R and S configuration at the carbon labeled in blue. Iodine is going to be number 1. Bromine will be number 2. Okay. And then we have carbon versus carbon. The carbon on the right has attached to it hydrogen, hydrogen, hydrogen. The carbon on the left has carbon, carbon, hydrogen. So the carbon on the left is going to get number 3. The carbon on the right is going to be number 4. So remember, to do R and S, we need the lower priority group pointing away from us. Okay, and so we could do that. We could just look straight down this path here, kind of like we were going to draw a Newman projection, and then that methyl group would be pointing away. So it would be 1 to 2 to 3, so this would actually be the S configuration. And since we only have one chiral center here, we don't need to put a number in front of it. Now, if you don't believe me, get a model kit out and make a model of this molecule and prove that to yourself. Okay. All right, and so for the molecule on the right, we're going to start. Let's see. Let's go ahead and find the longest path. 1, 2, 3, 4, 5, 6. 1, 2, 3, 4, 5, 6. Okay. And so if we go along the red path, we have 1, 2, 3, 4 substituents. If we go along the orange path, we have 1, 2, 3, 4 substituents. And I don't think it matters because along both paths we have an isopropyl and a methyl. Okay. And we also have a substituent at the 2, 3, 4, and 5 position, no matter which way we go. Right. So what we need to do is just go along the path that'll give us our first substituent, the first priority in the alphabet. So that's going to be the yellow path. So that will be 2,3-dichloro. So we're alphabetizing for the chlorine, that's C, okay? And then we've got an we're going along the orange path, right? Doesn't really matter. So that's 4-isopropyl 5-methyl, okay? Yeah, so 4-isopropyl 5-methyl, okay? And then our parent is hexane. But we also have 2 chiral centers here, so we need to give those R and S. Honestly, these examples are a little challenging. I think your book examples are not quite as challenging as these that this guy writing the PowerPoints comes up with, okay? So, fortunately on this first one, we've got a hydrogen going back, so we can give that priority 4. Chlorine coming out, that's number 1. Then we have a carbon bearing a chlorine and a carbon bearing 3 methyls. So this will be chlorine, carbon, hydrogen, so that's number 2. The one on the right has hydrogen, 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 that's number 3. So this is 1, 2, 3. This is R, okay? So the next center is at the 3rd carbon. Okay, and that one also has a hydrogen going back. So that's going to be chlorine's number 1, hydrogen's number 4. Then we have carbon versus carbon. The carbon on the right has chlorine, carbon, hydrogen. The carbon on the left has carbon, carbon, hydrogen. So this is going to be number 2. This one's going to be number 3. 1 to 2 to 3. This one is also R. Okay, so that is 2R, 3R, 2,3-dichloro, 4-isopropyl, 5-methylhexane. So these are a little bit challenging. And I have prepared some more here for us to work, okay? So on the top, this one's a little bit easier. Notice that the chlorine is at the first carbon on the right on the top one on A, so that's 1, 2, 3, 4, 5. So we're going to give that one carbon number 1. So this parent is pentane. It has 5 carbons. So that's going to be a 1-chloro and so we'd have a 1-chloro and a 4,4. I'm having trouble getting this pen to write today. Dibromo. Okay, but we have to alphabetize them instead of, they don't go in order of number, they go in alphabetical order, and by alphabetization we're going B versus C because the di doesn't count. So that's 4,4 dibromo, 1-chloro, pentane. Oh, we don't need a hyphen there, sorry. Alright. Oh yeah, remember that iso is the only prefix that counts for alphabetization, okay? Alright, this next one we can start numbering anywhere in the ring. We don't have to start at the end, but we do need to number the ring separately from any side chains. So we can give this carbon number 1. 1, 2, 3, 4, 5, 6. This parent is cyclo, because it's a ring, hexane. And so we have a 1-methyl and a 1-bromo. So that's going to be 1-bromo in alphabetical order, 1-methyl, cyclohexane. Okay. The next one, we have some stereochemistry. 1, 2, 3, 4, 5, 6, 7, 8 is a potential parent versus 1, 2, 3, 4, 5, 6, 7, 8. So it doesn't matter. Our substituents are both at the 4 position. Okay, and so that's going to be the parent of octane. Okay, so I've got 4-chloro, 4-ethyl. So that's 4-chloro, 4-ethyl, octane. And then we've got an R and S configuration we got to calculate there. Let's clean this up a little bit. get some room. Okay, so the chlorine is going to be number 1. Then we've got carbon, carbon, carbon. Okay. Well, I can tell you an easy way. These are just straight chains. The shorter chain is going to be lower priority than a longer chain. The carbon down here on this ethyl group has 2 carbons, okay, and so that one's going to be priority number 4 because we don't have a hydrogen here, right? This one here that I'm highlighting, making bigger, has 3 carbons, so that's going to be number 3. This one here that I'm highlighting has 1, 2, 3, 4 carbons. That's going to be priority number 2. Okay, so 4 is going back. That's convenient. So we have 1 to 2 to 3. That's going clockwise. So this is the R configuration. Okay, so this is R, 4 chloro, 4 ethyl, octane. Okay, so next we have substituents. 2 substituents at the second position. 1, 2, 3, 4, 5, 6 on a hexane chain. Okay, so that's 2,2-dimethyl 5-fluoro. Hexane, but we need to alphabetize them, so that's 5-fluoro 2, 2 dimethyl hexane. And again, we have stereochemistry at that carbon bearing the fluorine. Hydrogen is number 4, fluorine is number 1. This carbon on the right is number 2. The carbon on the left is number 3. So that's 1 to 2 to 3. So this is R. Okay, R, 5-fluoro 2,2-dimethyl hexane. Another thing about alkyl halides that we need to learn is a little bit about their structure. Carbons bearing the halogen are called the alpha carbon. So that carbon bearing the halogen is called the alpha carbon. And then moving away, we have beta and gamma. Okay? And these are important because we're going to have substitutions at the alpha position. That's the carbon bearing the halogen. And then we also have, what's wrong with my computer here? It's kind of spazzing out on me. Give me just a second for this to come back. Okay, there we go. Hope you can still see it. All right, and then at the beta, at the alpha and beta position, between those 2 positions is where we're going to get elimination. So we get substitution at the alpha position, and between the alpha and beta positions, we'll get elimination. Also, that carbon bearing the halogen can be considered as primary, secondary, or tertiary, according to how many R groups it has. So if it's a primary alkyl halide, it has 1 R group. If it's a secondary alkyl halide, it has 2 R groups on it. That means it has 2 carbons attached to the carbon bearing the halogen, to the alpha carbon, okay? And if it's tertiary, there are 3 carbons attached to the alpha carbon, okay? And there's also the possibility of having a methyl. This is just called a methyl alkyl halide, right? Methyl halide. Okay, so we have primary, secondary, and tertiary. Alkyl halides are often used as insecticides. They're also actually used as drugs. Okay, this one on the left here is DDT. Let's label DDT as primary, secondary, or tertiary. Okay, so this alkyl halide carbon, the sp3 hybridized, actually that is primary. It has 1 other carbon attached. Okay, it has 3 halogens. Alright, and so we want the alpha. This is the alpha carbon to that chlorine. This is beta. Okay, this is gamma. And the delta would be here or here. Okay, and same thing going the other way. And so next we have the this carbon bearing the chlorine. This is secondary. It's got 2 other carbons attached. Okay, and so we've got alpha, beta, and gamma, and then delta would be here. So right, so delta. All right, so going to the right, the other thing going to the left. So Alright, so what are they used for? They appear in a wide variety of natural and synthetic products, insecticides, dyes. Tyrian purple is a natural dye that has a halogen on it. Drugs, such as anti-cancer drugs, antidepressants like Prozac has a fluorine on it. Food additives like Splenda has some chlorines on it, nasty looking stuff, and many more. Okay, so organohalides are everywhere. They're in natural products. They're also in synthetic products and drugs. They're very important. They're also used to make plastics. They're just very important compounds. All right, so that ends our discussion on naming alkyl halides, and in the next section we will move on to some reactions.